Okay, welcome everybody to this first part of 2 wireless sessions. Quick introduction. My name is Rolf Leutert, running a small company over in Switzerland, dedicated to protocol analysis since more than 20 years, specialized on different topics, as you can see here, but my favorite is wireless. I was involved in one of the first huge wireless installation back in '99 when I was working for Swissair, the airline, and we were the first airline covering the whole airport of Zurich with wireless. It was not for the passenger at that time. No, none of the passenger had wireless at that time. It was the 802.11 native standard. There were no adapters available for PCs at that time. It was for the operating part of the airport, and we equipped a lot of cars which have been driving on the tarmac, and we saved them from going back frequently to certain terminals to get new instructions. So that was the first large, huge installation, huge with 60 access point. At that time it was huge. It was actually a 2 megabit throughput at that time. So that was the first standard 11 without any B or whatever existed at that time. Yes, then I learned Wireshark, started actually with the sniffer, and then switched to Wireshark in 2006. Started with first courses in Europe, and since then I'm doing training, but I also do troubleshooting, and that's the part which keeps me also challenged, because these are the complicated situation when the customer calls me. They have replaced what you can replace very easy. So, and out of this part, a lot of trace files come into my classes, into my trainings, either on TCP or on VoIP, or as you will see here, on wireless. So the trace files which you are going to see, most of them are from real problem situation. Yes, what we learn here in the first session is that we have to care again about layer 1 and 2 in wireless. So this is different from Ethernet. Wireless was, at the very beginning, was called wireless Ethernet, but that was just a marketing term. We will find out it has very little to do with original Ethernet. It's very different already on layer 1, as we will see, and it's also different on layer 2. That means all the framings. That will be the second part then. So how can Wireshark help us to isolate wireless problems? It's not that easy as in wired. You cannot just plug in, and you hardly can use your internal wireless adapter. We will discuss why this is the case and what you can do. And Wireshark is not suitable for layer 1 at all. You won't see non-wireless devices which you have to care about. So you need to have some other tools which we will go through it. We will learn about special headers in the wireless frames, pseudo headers, or we will also learn about different number of address fields, very special. We'll look at this. Wireshark then, of course, comes into the game when we talk about layer 2. And we will, of course, have possibility to specify Wireshark with additional columns, with additional profiles, and I will recommend or suggest what you do here. So it's really very demanding here. Layer 1 is normally not a topic anymore in Ethernet. If you have a problem layer 1, you replace the cable, or you take another port, or you send somebody to measure the attenuation of the cable, but it's much more stable. Once you have laid a cable or a fiber, once it's running and once it's tested, it hardly ever breaks. This is not the case with wireless. You can do a very good installation, an excellent installation. The next day, the neighbor beside you or above you starts with his own wireless, and it will interfere or may interfere with your wireless. So I always, even though I love wireless, I always recommend, if you can use the wire, prefer the wire. It's much more reliable, it's more secure, it's faster. So use wireless if you really need mobility. That's the big advantage of wireless. And of course, you know yourself, a lot of new components don't even support wire anymore. All these pads and all these smartphones and so on, they need wireless, but if you have both choice available and you want to be on the safe side, then wire would be the much secure choice and much more reliable. But anyway, that's what we have to look at. The layer 1 is how the cell, how the frequencies are used by different devices. And we must realize that there are more devices than only Wi-Fi. Wi-Fi are the standard devices, which we know we use a framing, but we realize that everybody else can use layer 1. Legally use, and they can interfere, and they will interfere with your wireless communication. So that's what we are going to look at first, the layer 1. How can we detect, how can we recognize what is on in the layer 1, what makes the cell busy. Then, as I said, here Wireshark comes into the game. Wireshark is the tool if you're using framing, and we are going to cover the most important frames here. That's again very different from Ethernet. We have a lot of so-called control frames, up to 15 different control frames besides the data frame. On Ethernet you more or less see all data frames, so no frames are there if nobody is sending anything. That's very different in the wireless cell. We will see a lot of frames without data, just to control the air, to control the access, and these are the frames you actually need to know for troubleshooting, like beacons, authentication, probe requests, request to send, clear to send. We are going to understand most of them, what is possible in such a short time. Normally, the wireless class is at least 2 or 3 days. It's so many details to dig down. But still, it's good enough to understand the most important elements of wireless. Again, you have to be different when you talk about wireless. Wireless is the general term for all devices using non-wires, but a lot of them are non-Wi-Fi. Wi-Fi is the term for devices which are using a protocol according to 802.11. So that's the Wi-Fi label reserved for. All other devices still using the same channels are still wireless. They are also wireless, and they can interfere, and they will interfere, and they are called non-Wi-Fi devices. But the bands are free for any use. 2.4 and the 5 gigahertz are free for any use, as long as you keep to the country regulations regarding the transmitted power, which is in Europe it's 100 milliwatt in maximum. So you don't need any license. It's a license-free band, and anybody can use and will use. So it depends on the area you are. If you're in a private home, in your home, then you probably have a lot of these devices around you. We will see how they can be detected and what they can do with your wireless network. One more time, Wireshark cannot detect these non-Wi-Fi devices. It's not possible. You need a so-called spectrum analyzer, which works on layer 1. And there are different tools available, more or less expensive. One of the most frequently one is this Wi-Spy, which is available as an additional device which connects to your USB and comes with a software. It's from MetaGig. And if you're looking for non-Wi-Fi devices, then this may be the tool, and I show you how it works. So this is how the spectrum would look like. Here we have one channel used in the 2.4 gig band. You heard that we have different channels here, which was a little bit misleading at the beginning because we could not use all the channels. That was, let's say, wrong information. They learned from it. In the 5 gig, they will only let you configure channels which you can be used, like 36 and 40 and 44, so-called non-overlapping channel. A lot of people which are new to wireless do not realize we have 11 so-called channels, but actually we can only use channel 1, 6, and 11 because we cannot use overlapping channel. So you see here an access point which is set to channel 6, and you can easily see that it actually also using channel 5 and channel 7. We have 20 megahertz bandwidth, and the channels are only 5 megahertz away. So we are using 4 channels actually, and that's something you have to realize. That's why you see often the pattern 1, 6, 11 in the States, or in Europe we are going up to 13. So we have 2 more channels. Then you see sometimes a pattern 1, 5, 9, 13. But if you want to be compatible with Wi-Fi from the States, then 1, 6, 11 is the pattern. Here are some patterns of non-Wi-Fi devices before we have a look at the real-life Wi-Spy. And you easily can see that they are using the same channels, but in a completely different way. They are using proprietary information. They may be streaming continuously. You see this here in the lower part. The lower part is a so-called waterfall statistic. And if it's in red, then it means you have more or less 100% duty cycle. It means the sender is continuously. So here, for example, the famous microwave oven, which is more or less covering the whole 2.4 gig. And now you may say, okay, I don't put my access point on the microwave oven, right? But actually, one of my largest customers are hospitals. I have 3 hospitals in the area of Zurich with more than 3,000 access points each. And they have a lot of microwave oven in on the floor, right, for the nurses preparing their lunches and yes. So it may really interfere with your wireless. The good thing is this is only in 2.4, so microwave is not working in 5 gig. So that's the good message. So more and more enterprise grade wireless are moving to 5 gig, which we'll look at in a minute. So all these low-cost wireless devices like remote control of model airplanes, wireless guitars, good luck, most of them are in the 2.4 gig and not yet in the 5 gig. The 5 gig has more regulations, more restrictions. The chips are more expensive at the moment, but it will be a question of time until these components are also available in the 5 gig. Here, another view of so-called channel bonding. You may have heard the term. It has been introduced with the 11N standard that you can use multiple channels kind in parallel for transmission. AC even goes up to 4 channels, the AC standard, which I will show you later, these different standards. And here we see with this Wi-Fi 4 channels bonded, so 36, 40, 44, and 48 bonded into one channel, which of course gives you more throughput than, but of course the channels must be available. So let's look at the live analyzing here in the room. So I have this Wi-Fi adapter here connected, and it comes with a software called Channelizer. And let's have a look at the 2.4 band first. So you see here again our channels, and you see that obviously here in the room channel 1 is quite busy, so it just stopped working, I'm realizing. So it's not updated anymore. I think I disconnected, yes, I disconnected. Okay. So what you see here on top is the signal strength. Signal strength is measured in dBm, decibel milliwatt. So we are going to talk about this later. A good signal, a strong signal is around -60. And it's becoming weaker with a higher value. Below down, what we see here on the ground, that's what we call noise. That is activity which you always have from any kind of devices in the air. So the noise is, if it's a good value, it's below 90, 95, or can even go lower depending where you are. In an industrial environment, it's probably higher from all the electric components and devices you have available. The signal is good as long as it is 20 dB away from the noise. So even 70 can be a good signal, -70 can be a good signal as long as the noise is not above 90. So the distance here should be 20 dB, which is a factor 100. If you have a very good receiver, then 17 dB is good enough, which is factor 50. 3 dB is always half or double, so that's what you can see here. Below you see here the so-called Waterfall, which I announced, And here you see we had some activity here in channel 6, but it's not bad. Green means we are below 80%, 60 to 80%. If it turns red, that would mean it's very busy. So here you can always still have free space available. You see also here in this room, if you would have to place another access point, you would probably use channel 11, right? Because that's the only one which is available here. Here we see some disturbances. This is something which is non-Wi-Fi. We cannot tell at the moment what it is. Anyway, it is out of our range, so we don't care. But it is some, whatever device, maybe some of these amplifiers or whatever. Below here, they offer us some so-called signatures. Some devices have the special shapes of using the frequency band. So if you see a strange shape and if you would like to find out what it is, then you may click on one of these examples here. You may double click and then you can draw it up here and try to find a match. To be honest, under us, I never found a match with one of these signatures, but it still show you an example where WiSpy could help us to isolate the problem. So let's quickly have a look at the 5 gigahertz band. This tool is capable of looking at both bands. You know that in 5 gigahertz you have much more channels. In 2.4 we have 4 or 3 non-overlapping. In the 5 gig we have, depending on the States or Europe, in Europe we have 19 non-overlapping channels. So you can use them all, 19. If you want to look at the full band with all channels, then you can do this. Mainly used are the 4 lower channel, 36, 40, 44, because these are the channels with the least restrictions. The other channels may have restrictions like dynamic frequency select. That means the access point has to listen to other users, like mainly weather radar, and should change the channel if it receives some signal on this channel. So this is not the case for the lower 4. That's why most of the devices these days are using this lower channel here. Be careful if the device claims to support A standard. A is the general term for the 5 gig band, but it does not necessarily specify which channels are supported. So be careful. I had bought some devices which turned out they only support the lowest 4 channel and could not connect to an access point working on channel 100, for example. So here you see again that obviously here in this building there's some activity here in channel 100, channel 112. We can later on try to look at this with Wireshark. If this is a framing based, just looking at the shape, it looks to me like it's a framing based transmission. You cannot say this with this device. This device is just showing you the shapes on layer 1. But you can still zoom in. Let's say I would like to see only the lowest 4 channels. Then I can say, okay, show me only here the UNI band with the lower 4 channel, and then it would spread it all a little bit and show it. So we have very little activity here. So obviously people are not connected to too many to this upper band, and activity is also very low. So if you would make a file transfer now on one of these channels, then you would see here immediately the turning red, the load duty cycle going up to higher value, 80 and more percent. Okay, so we have, as it seems now, no foreign, no non-Wi-Fi devices, even, let's go back to the 2.4, even though we have some strange signals in here, but that's absolutely normal. For example, Bluetooth, my Bluetooth mouse here, Bluetooth is using a technique called frequency hopping. So all these small little spikes you may see here is maybe used by Bluetooth. Bluetooth is just hopping through all the channels, but only for a very short time, which will not significantly disturb your communication. So again, it's kind of hard to say if a disturbance, if a non-Wi-Fi device is having an influence on your communication. My point is I normally do not start with Wi-Spy by searching problems. I start with Wireshark, and I told you Wireshark is not able to see layer 1, but I'm still able to tell with Wireshark if layer 1 is good or bad. Because if I have a lot of frames with FCS errors, bad frames, then I can assume I have a problem on layer 1. So my first tool is Wireshark, and then if I find out there probably is something on layer 1, then I use this tool here. Any question on this so far? Yes, I promised you some real-life examples from my troubleshooting activity. And this is a classical case here where we had problems with layer 1, but we didn't know it at the beginning, of course. It was a customer which has a huge distribution center. You see here all the containers. They have 2 cranes to unload railway, the railway to trucks, and they provided me with the wireless layout, so you can here see the Google view. So they are connected here to the railway, and the railways come in here, and then they are unloaded with 2 cranes. They are unloaded here to a lot of these trucks or containers. And actually they could use only 1 crane, crane number 1. Crane number 2 had no connection to the main building. And the main connection was used because the driver of this crane had to know where to get the containers and where to put it. And this was done with wireless connection, but it was not usable, especially in the corner here. When they drove towards the center, then the crane was connecting to the cell here, and then it was okay, but it could not work on this cell here. So they added a cell, another one, tried to improve the situation, but it didn't work. So what we did, we went here and made some measurement in this area. It is in the 2.4 gigahertz area, and it turned out that we had a lot of bad frames with Wireshark. How can I detect bad frames with Wireshark? We will see later that in wireless, which is again different from Ethernet, every frame in the air is acknowledged with a specific acknowledge. So a control frame coming back, when we send a data frame, the receiver has to send an acknowledge back, whether it's the access point or it's the end client in both directions. If a frame is not acknowledged, the sender will resend the packet, only in the air. And the frame which follow after the first one, they all have the so-called retry bit set. So it's actually quite easy to find out how good your transmission is. You just do a filter on all packets with the retry bit set. And if this goes up to 10, 20, 30 or even 70%, that means you don't have a good throughput anymore, right? 70% of the frames have been retransmitted. So that's what you can do with Wireshark. Not more and not less. Now you can assume something must be wrong on layer 1, but you cannot tell what is wrong because we only see frames with Wireshark. But you see bad frames, FCS errors or whatever, and you see the retransmission. And here you can see in IOGraph the red, the black line are the total packets, and the red one are the retransmission packet, the read-write packet. And that's when I used WiSpy to scan the 2.4 gigahertz and find out that there are strange signals, and more or less in all channels, right? You see here, this signal here makes it impossible to use channel 1. This one here makes it impossible to use channel 6, and this to 11 or whatever. These are non-Wi-Fi signals. You can tell from the shape. You've seen a shape before with the 20 megahertz. That's all you can say. So, and what you also can say is they are quite consistent. You see here the red line going through. So they have almost no break in between. They are just standing, especially here, nice to see. But now that's the problem, how to find out what it is. That's the next step. The first step is to find out there is something, right? So what you can do now is you can either have a directional antenna to find out which direction the signal comes from. I didn't have this, so I just have this normal dipole antenna here. But what you can do now, you can move around and see if the signal becomes stronger or not. And that's what we actually did. Because if you move away from the signal, then the so-called amplitude here goes down. And if you closer, it goes up. And that's how we found out where the signal comes from. The first question, of course, was, is it from the customer's campus? Is it something which, is it something which is on the campus? Is it a device from the customer itself, or is it coming from outside? If it's coming from outside, you have limited possibilities. You're not allowed to do public analyzing, right? So we find out it's coming from that corner. No wonder, because they have found out this already. And if we move towards the public railway, we find out that the signal comes somewhere from here and from that area, which we were not allowed to visit. But in these cases, you can involve public authority, which we did. We involved the Swiss authority because you can ask them to find out if this signal is still legal. For us, it seems to be too strong. If it's below 100 milliwatt, there is nothing you can do. Again, it's absolutely legal, but we have the impression it was too strong. That's why we involved the radio authority to check with us. And actually, they came with their special equipment, probably 10 times more expensive than the one I had, but they find out the same shape, of course much more precise than probably Wi-Fi, but that was no problem, and they even could isolate the source of it. It was near the public rail. Beside the rail they have a so-called traffic monitor induction loop, and of course this was defect. It is not a normal behavior. It had some defect. It was sending out these signals all the time, but not right from the beginning, because at the very beginning crane number 2 was usable, but so it had some kind of defect. So it took a while to get this repaired. The customer didn't want it to wait, so we were looking for a workaround, and the workaround was just to switch one of these access points to 5 gig, which is no problem as long as the client supports dual band, and most clients today do it. So we just switch this access point to 5 gig, and if you move the crane over here, it goes back to 2.4. So as long as you're using the same SSID for both frequencies, the client itself will scan and find the right connection. So this was a workaround because the 2.4 gig was disturbed. We switched to 5 gig. The one here could have been removed afterwards. We didn't need that one, so it was switched here. So that's a case how you can detect and how you can use and have to use layer 1 tool. There are other tools around, and I heard that more and more in the future also adapter access point will be able to do spectrum analyzing, but not normal adapters. Normal adapters in a PC are not able to do this analyzing. It requires more hardware to do this. But still there are so-called scanners around, which you may know and heard of, and which are valuable, but you have to know what is their restrictions. They show you all the wireless around, including the names, including the strengths, and whatever, and you have the impression they do something similar like Wi-Fi. It's actually not true, and I show you in a minute. But I still also use them. For example, here, one of the free tools I have here on my Mac, it's called a Wi-Fi scanner, and it does exactly the same job. What it actually does, it is showing you a list of all available access points, and again this is live, so you see a lot of hidden ones here which do not propagate the SSID. You see some activity here in the 5 gig band. You see even channel bonding because if you see the width here, this is a normal channel, 20 megahertz, so this looks like 4 channels bonded. You also can see this up here. Probably hard to read on the screen, but here you can see the channel width, and there is one here with 80 megahertz, and that's the one here with that name. So these tools are quite helpful to give you an overview which channels are crowded and which are available. It doesn't show you the load on the channels. So we've seen before with Wi-Fi that the channel 11 was hardly used, but if you look at this, you still see here some SSID, but obviously most of the users are connected to 6 and 1, so you don't see the real load here, you just see where are SSIDs. You have multiple SSIDs in the same channel, which is possible, as long as the difference is 20 dB, they will not disturb each other. But the ones which are close together, they share the bandwidth. Remember, we have a cell system, we have a shared media. I'm going to talk about this in a minute. So you cannot use all this SSID at the same time, only one at a time. So what can these tools do for you? I just made you a list of a quick list of a few popular of these free tools. Mostly are free, run on your phone or run on your PC. But they have one limitation. They all base on the availabilities of the so-called beacons. Now we are going one layer higher, talking about framing, and one of the frames you will see most often is the beacon frame. Beacon frame is sent out by access point 10 times a second per SSID. So if you have multiple SSID which you can install on the same access point, then it's sending out 10 every 100 millisecond a beacon per SSID. The information in the beacon can be used and will be used by these tools. So if the beacon is destroyed by something which we saw before, then this tool will not show you anything, right? Because if the beacon is destroyed by a CRC error, it will not be forwarded to the application. It will be discarded by your Wi-Fi card. And then what would happen, let's quickly go back, then what would happen is that all this would disappear, for example, in a specific channel. So these are not real scanners in a way of spectrum analyzers. What they actually do, they scan through the channels and listening for beacons, which is good enough if you want a list of what is available. But again, they rely, these tools rely on the fact that layer 1 must be working. There should not be interference here with any. So if I turn on a micro oven now, then I would see all this here disappear. After a while, they will just be deleted because the beacons are not decoded anymore. So that's what you have to know about these scanners. They are still very helpful, but they have their limitations. The beacon, yes, I was mentioning, the beacon contains a lot of information from the access point. It's not only a signal of presence, it also to distribute the capabilities of this access point. Supported speed, supported standard, required encryption. That's all in the beacons. We are going to look at it in more details in the part 2 of this presentation. So you see here in Wireshark you can add different columns, which of course is really important. And you see in which channel here in the A panel 100 we see an access point broadcasting a beacon frame. We see the signal strength, which is very good. We see the noise, and we see the speed. That's another specialty of wireless. You have different speed in the same cell. So one client can connect with 54 when the client is closed location to the access point, whereas another client at the end of the cell may only have a connection with 6 megabits. So of course, the more clients you have which are at the end of the cell, the lower is the throughput of the cell, right? because 6 megabit means you need longer to send your packet. So this is one of the also things which are very different in Ethernet. We have different speed, but not on the same network. We have either 10, 100 gig or whatever, but one link always has the same speed. Here we can have different speed in the same cell depending on where the client is located. The access point keeps track of all his client and knows with what speed the client last arrived and will use this speed to talk to the client. Okay, let's talk a little bit more about capturing. How do I capture frames? Again, I mentioned already, in Ethernet it's very easy, as long as you have a built-in Ethernet card. You just run capture, Wireshark, using WinPCAP. WinPCAP will detect your adapter, you start running, start capturing. This is not so easy with your built-in NIC card, especially not under Windows. So the question is, am I able to use my internal wireless card to capture traffic? And it depends on a lot of things like what operating system, what hardware you have, what adapter, and so on. And especially Windows is very limited. It captures only broadcast and your own traffic. That means you don't see the traffic of the others in the same cell, which makes it kind of useless for troubleshooting, right? And even more important, it will not show you all the management and control frames. So no beacons, no request to send, no nothing. And these are the important frames for troubleshooting, as we'll see. And even if you have data, and if you are sending out data and receiving data, this data will be displayed in a fake Ethernet frame format, which I'm going to show you. So it's converted in an Ethernet frame and then shown on Wireshark. You can easily try this, start Wireshark, look at your local network card, press start, and you will see these fake Ethernet frames, and you will not see any other traffic or other beside a broadcast and your own. Some OSs like Mac OS have some other possibilities. For example, I'm running here Windows over Mac, so I can show you here that if I start Wireshark on my Mac OS, I actually have the monitor mode here available on this Wi-Fi card. Monitor mode is important and promiscuous mode is important. And if I start here, I can see these frames. I see the beacon frames. I see all the traffic from others. So that can be used. I can even add signal strengths, noise and everything. So what's the restriction here? The restriction is I see only one channel. The channel which I'm connected at present. But it's maybe good enough for many situations. And we'll see how we can cover the other situation. So this is pretty normal. I just stop here and then I see the different beacons. So I was now connected in channel 48. So I see all the beacons in this channel. I see ARPs and everything as long as it's not encrypted. So let's go back here to this list here. What if I need to simultaneously capture in multiple channels? When do I need this? If you need to troubleshoot roaming problems, roaming or correctly handover is the process of changing the cell during operations, seamless roaming. So the session, TCP session, everything should stay up. And in reality, quite a few problems have to do with roaming. I show this in the second part also. And these problems can only be captured if you are using multiple channels, because you need to then capture multiple channels simultaneously, and that requires hardware. And that's where Sherald actually, when they started CASE, came out with the first hardware product called AirPCAP. Anybody heard of AirPCAP? Yes? It's not continued anymore. It has stopped. It was then till January 1st by Riverbed. It's not available anymore, and it does not support USB 3, which is the most hindering part here. So here with AirPCAP, you could have 3 in a hub, and then select channel 1, 6, and 11, and then you could have 3 channels simultaneously, and the same for the 5 gig, of course. So yes, this is possible, and I will show you what hardware is available today to do it. Can I decrypt data? Most data packets are encrypted this day on wireless, and yes, you can under certain requirements. You need to have the shared key available, and you need to capture the negotiation process at the beginning, because the shared key is never used to encrypt. It is merged together with a variable value which is negotiated at the beginning in a so-called 4-way handshake. And if you capture that with Wireshark, then Wireshark can make the session key and can decrypt data, but only with the shared key, not with certificates and so on. More information you find here under the link. Yesterday, Thomas Trapp had a good presentation how you can use other tools for capturing. Anybody followed him yesterday morning? Yes. So if you want more information how to capture with what equipment, then you may download his presentation. It was very detailed. I have some list here also, and I find an interesting tool, but again, it's only for Mac OS, the Air tool, which I would like quickly show you. The Air tool here allows that you can use Wireshark for multiple channels, but again, it's only scanning through the channels. So you can use your internal card here, your internal wireless, to scan through the channel with the Air tool, but it's not for roaming purposes, because again, if you're scanning, you're just hopping between the channels, and I can quickly show that. You can say capture all 2.4, and then it captures from different channel, but you have to disconnect from your favorite wire access point before you can do this. So let's quickly stop here. And it opens Wireshark and shows you different channels. In this case here, we were scanning through channel 1, 3, 4, 6, you see here, scanning through the different channels. So there are tools available depending on what operating system you have. Again, Windows is the most restrictive one. You may have possibility with a new driver called NPCAP. Go to these links here to verify what's possible. And another way of capturing may be using existing access points. More and more access points have a capture feature built in, so that you can remote access and start capturing. Even some which are cloud controlled, like you may heard of Meraki, bought by Cisco, Meraki is a fully cloud-controlled access point, and you can access it from anywhere, and they have a built-in capture facility. You can even select to capture on the wireless or on the wire side of the access point, and it creates a PCAP file. You can select a filter even, and then you can download it with the Wireshark and open it like any normal file. So use existing equipment, but some access point have to be switched into a monitor mode, and then they are not available anymore for the users. That's of course not what you really want. In this case, Meraki can do both, do capturing and still do the job at the same time. So be careful with this check. Other go out with a special access point just for measuring, but again, you have only one channel available. If this is good enough, then that's okay. I was talking about this faked Ethernet frame. The frame which you look at with, for example, Windows, they look like they are Ethernet frame. You cannot differentiate. The IP address is okay, the MAC address is okay, but these are fake Ethernet frame because in the air, we will see later on, the frames look very different. They have a different header, they have a so-called wireless header, and we have, and that's really amazing, we have in wireless, we have different frames. Some have only one MAC address, others have 2 MAC address, others have 3, and others have 4. I'm going to explain this in the part 2. And here you won't see the difference. You also won't see any acknowledges, the one which I mentioned. These are all control frames. They will not be visible without the special hardware and without special driver. So that's the limitation you have with this. Yes, let's talk about additional headers added to what you capture from the air. Remember, we have a shared media, so it's very easy to capture. We don't need a span port or something like this. You just tune your adapter to a certain frequency, let's say channel 1 here in this room, put it up and can immediately receive with the right driver and the right hardware all packets in this cell. And as we have a shared media, only one station should send at a time, and you can capture this and store it in a file. But in order to have more information about the signal strengths and other information required, a lot of these tools add a so-called pseudo header. So let's look at a trace file, at a real wireless trace file now. And you will see, for example, here a beacon, and you will see that you have additional headers here, like radio information. And this information is not part of the frame transmitted over the air. This information is added by the receiving adapter. That's why we call it pseudo header. It's not a real header, but it's very important information which then can be used to add additional columns. You don't find the data rate in a frame. You don't find the channel in a frame. You don't find the noise and signal strengths in a frame over the air. These are values which are only from this specific point where I'm measuring, and they are added by the tool which you are using. They even are added by this adapter here from the from the Apple, from the Mac. So it's also adding this information. So it's kind of a standard that if you are capturing wireless and if you are not only showing fake Ethernet, that you provide this information. And this is really important for troubleshooting because it allows you to find out if we have a signal problem. Do we have a signal to noise ratio problem? Remember, this value should be at least 20 dB in difference. Here it's very good, very strong. We have almost 70, 71. So that's something which is required here. And these are this additional information. There are two types of header established, radio or PPI. Some tools allow to select which one, but most of the tools are using the radio tab header. That's the most popular one. They provide not exactly the same information, but they both have the same principle. They add information and they store the information with the frame. So whenever you open a trace file, the information is available. So they actually add additional like metadata to the data. Like the timestamp you have on Ethernet, right? The timestamp is also added by your adapter. Here we have a timestamp also, but we have much more additional information. So this makes troubleshooting really helpful in wireless. Here the comparison between the two headers. Here you see the radio tab header, and here you see the PPI header. Wireshark people added this radio information header, which is a summary of the fields of PPI. So if you make additional columns, I recommend that you're using the information from the radio information field and not from the tabber, from the radio tab or PPI. Otherwise, you need two profiles, one for radio tab and one for PPI. But if you take the information from this field, then it is the same field for both kind of headers. So again, that's very different from Ethernet and is important for. So here you can see what I added here. This is the recommended. I would like to see what signal strength, what noise level. I would like to see what speed. Beacon frames are always sent in the lowest speed. So if the lowest speed in a cell is defined 6 meg, which is in the A band, the lowest speed, then the beacons are sent with 6 meg, because the beacons should be heard by all the clients. But if we later look at data, then you will see different speed per client. Again, the clients close to the access point will use 54 or even more. So that's what you see here in the profile. You also can provide different channels with different colors, which makes sense for analyzing. It's just in the color profile. And then you see that stations are actually scanning through the channels. Each station is scanning through channels with the so-called probe request. That's another control frame. It's kind of asking what stations, what access points with what SSID are available. And here you see I made a capture with 3 channels, assigned a different color per channel. So this guy here, this Intel guy, was scanning through channel 11. Of course, it was also scanning through channel 1, 3, 2, 4, which we don't see because I was only capturing in 1, 6, 11. But you see here how it's scanning through the different channels. Let's have a quick look at layer 1 here. For the last time, we will see in the next part that every packet in the air, I mentioned it already, every packet in the air has to be acknowledged, explicit by the receiver. But how can you grant that in a shared media environment? an acknowledger always come through, not another data packet. And this is done very clever with different so-called frame gaps. That means, and you may have to Google for this, it's becoming quite confusing. That's why I made this list here with the most important different gaps or interframe spaces, how they are called. A station which is receiving a packet, let's say this station 1 here is the receiver of this running packet from the access point. So as soon as the packet is finished, transmission is finished, the station is checking the frame check sequence. We do not want to acknowledge a bad frame, right? So the last 4 bytes here are the frame check sequence. If the frame check sequence is okay, this guy needs to send an acknowledge, otherwise the frame is retransmitted. So the problem now, this guy should not have to compete with other stations waiting to send data, and that's done with different small spaces. So this guy here can already, after CIFS, which depends on what standard, but it's the shortest frame, this guy can send the acknowledge. As soon as the media is occupied, this guy here has to draw back again. These 2 stations would like to send also. When the acknowledge is gone, the media becomes free again. Now these 2 guys are competing, right? They both have a data to send in the buffer. Now these guys would collide if they start at the same time. So what they do, they have additional random number of so-called slot times. So done with a dice. So this one was having random number 3 slot times. This one was random number 6. So they have to wait diffs and in addition the slot times, which you see up here. And again, station 3 now realizes that the medium becomes busy, has to wait back, and again the story with the acknowledge, and then finally, after the 3rd trial here, this guy is able to send. So that's how the media is shared among station, and if you look at this, then you wonder that it still works if we have 10 or 20 stations, because it looks like they compete very much with each other, which they actually do, but it's all in a very short time, so that's, yes. Okay, let's quickly finish here. RPCAP, I mentioned, is not available anymore. We have an announcement here. There's a new product available for hardware, hardware for multiple channel. It's called Wave Expert. It's brand new. The people out there at the SCOS booth can show it to you. It is very unique in that it supports up to AC standard Wave 2 and multiple channels, and of course it has its price. It's not for private use, you can see this, but if a company has large wireless network like 3,000 access points, then you need to have some equipment available, and it's connecting through a PC with Thunderbolt 3, so it's having the 4 modules in there, and I will show a little bit about configuration in the next part, just a few screenshots, and then how it looks when you capture with it. WiSpy was covering only, not WiSpy, RPCAP was covering only 300 bits per second in maximum, and this box is going up to 1700 AC Wave 2, which is of course the actual standard which is implemented. In the next session, we have to break here. In the next session we are going to talk about more about this management and control frames. which part of them we already covered. But these are the ones you have to understand, you need to understand to troubleshoot wireless. Of course, you also have data packets, but I always say if you see data packets, then you probably have solved the problem. If you don't see data packets, then you may find out by looking at these frames what is causing your problem. Okay, that was it for the first part. Any questions left? Okay, thank you very much. Have a break and welcome back to the part.